Yeah, good morning. Welcome you all to this next lecture on the inorganic chemistry of life, principles and perspectives. In the previous classes, we have learned quite a few things, particularly the main theme of all what we have learned is that a metalloprotein, the metal ion is present like a metal ion complex, and the protein surrounds this and then provides a property that is required to exhibit. This maybe probably can be seen to recapitulate what I said earlier. A metalloprotein is a protein plus metal ion, and a metalloenzyme a protein plus metal ion complexed plus function. So, this is what I wanted you to keep in mind, is that the metalloenzyme, the metal center, acts like a coordination complex, but not like the one which is present in the test tube or usual aqueous medium, but the properties have been very well modified by the presence of the protein, because of the protein conformation, because of the protein hydrophobic, hydrophilic, various aspects of this. Then we have also looked at certain biological aspects related to this biomolecules, particularly the proteins and the nucleic acid. Then we also have looked at a few biochemical processes like the protein synthesis, metalloprotein synthesis, etc. So, in this particular class, let us look at some coordination characteristics of these. The reason is that you are going to look at the metalloenzyme, a part of the metalloenzyme which is in the vicinity of the metal center as the coordination complex. Therefore, it becomes essential for us to look at a few details. I am sure most of you, even those who are studied the chemistry at 12th level, must have studied certain coordination chemistry aspects, but nevertheless this particular discussion now will give you a recapitulation of what a coordination complex, what are the things that we need to remember in order to understand the metalloenzymes and metalloproteins. So, let us focus at the slide shown over here, coordination complexes. So, obviously in any coordination complex you have a metal ion, and the metal ion is surrounded by the ligands, and that is what is basically is referred as a coordination complex. Then the metal ion has certain charge, certain oxidation state, and ligands may have a charge, may not have a charge either. So, therefore, the overall charge is defined by or determined by the oxidation state as well as the charges present on the individual ligands. So, it is a summation of all this, which I am sure you are all aware of it. In this particular example, we have a central ion is a cobalt, there are 6 ammonia, and you know ammonia is a neutral ligand, therefore, it is charge is 0, the cobalt is in cobalt 3 plus, the total charge is 3 plus as the cobalt oxidation state. So, this is a coordination number, this is a ligand, this is a metal center, and you take another example somewhere here shown over there, cobalt with 4 ammonias and 2 chlorides and 1 chloride outside this bracket. I will explain you this. As far as the kind of a coordination complex definition of the Werner, you have those ligands which are directly bonded is called secondary valence. It is not secondary coordination sphere, secondary valence, and those which are outside this is called primary valence. Okay. So, this will compensate the charge, +1 it will be -1, and this basically tells you the 4 neutral ligands, 2 anionic ligands, and there is a positive charge, therefore, cobalt is 3 plus. So, cobalt oxidation state is again 3 plus, and the total coordination number is 6, and it has 1 plus charge and then compensated by chloride ion outside. So, in this what we have seen, the ligand binds to the metal center. So, L to M, this is ligand binds to the metal center. Ligand can be neutral, as I said, ligand can be anionic. Okay. There is hardly any cationic kind of a thing, but there are some extended kind of a cationic, may not be at the center where it binds, but somewhere else but such special cases let us not worry in this particular case. In this particular course, as I mean. Okay. So, you can have a ligand bound to the metal by one connectivity, single connectivity is called monodentate, or a ligand just like this may be connected to the metal center by a 2. So, therefore, it is called bidentate, or it could be connected by more than 2, tri, tetra, penta, and even polydentate. Okay. So, ligand can be monodentate, bidentate, tridentate, tetradentate, variety of things. A ligand could be neutral or anionic kind of things. And some examples, when you have some free time, you can sit and look into these ones. These are all monodentate, that means they bind to the metal center through only one connectivity, single connectivity. Okay. And these are some examples for bidentate. You see the nitrogen here of the amine, nitrogen here of the amine, both of these can bind. So, therefore, when both of them binds, it is called the bidentate. Even if though there are two centers and only one binds, then it is still a monodentate, it is not, cannot be a bidentate. Okay, for example, bipyridal, there is two nitrogens, if both of them bind together simultaneously, it is a bidentate. Then you have a phenolphthalein kind of thing, and you have other kinds of ligands too. You have more dentates here, one amine, another 3, it could be tridentate. So, you can have oxo ions. So, therefore, this can be, and here you have a carboxylate moieties, 4 such carboxylate moieties, and one nitrogen, another nitrogen. It is a very famous ligand, a famous chelator which is called EDTA. So, EDTA is a famous chelator because it is non-selective and it can bind to many metal ions and chelate it. So, the highest coordination number for a EDTA is 6, 1 here, 2, 3, 4, then 5 and 6. Sometimes some of the carboxylate can act either as a monodentate or even as a bidentate, or it can act as a bridging bidentate too. Okay. So, these are the some things which you need to learn. So, having such a kind of a connectivity to the metal center, this will lead to different kind of a geometries. Okay. Let us look at this particular table with a little focus. There are 2 coordination number, 3 coordination number, 4, 5, 6, 7. There are coordination numbers beyond 7. Are they not possible? They are possible. They are mostly possible for lanthanides and actinides. And as you know, none of the essential element is a lanthanide and actinide. But we have some elements in 4D and 5D like molybdenum and tungsten. Therefore, we need to consider up to 7 coordination, but not beyond. Therefore, for this course I have restricted the table only up to the 7 coordination. This does not mean the coordination complexes exhibit only 7 coordination maximum, that is not correct. Okay, let us now look at one by one. The complex geometry with the 2 is linear. You can also have bend, okay, like in water, HOH kind of thing. We are looking at the inorganic examples, AgCN2 minus, etc., Ag ammonia twice plus, these kind of things would give. Then trigonal planar, HgI3 minus, then you have a tetrahedral, then a 4 coordinated, and another geometry of the 4 coordinated most commonly shown by the transition metals is square planar. So, some of the transition metals prefer to be square planar, particularly those of D8 kind of a systems would tend to give more of a square planar. This does not mean other D configurations do not show, that is not the correct deduction. D8s most often tend to show the square planar. The reasons are not explained here, because that forms a hardcore inorganic chemistry explanations, coordination chemistry explanations in that. Okay. So, tetrahedral and square planar. When it comes to the 5 coordinated, you have a trigonal bipyramidal, you have a square pyramidal. Okay. So, there are 5 coordinate, and both for the square pyramidal and trigonal bipyramidal. When it comes to the 6 coordinate, you can have the octahedral, you can have a trigonal prismatic. Octahedral is nothing but trigonal antiprismatic. So, antiprismatic and the prismatic, there are 2 kinds of things there. Okay. So, the corresponding examples are given over here. And for 7 coordination, then you have a pentagonal bipyramid. What does it mean? 5 in one plane, the 2 one above, one below. So, 5 plus 2, that is 7. So, pentagonal bipyramid, okay. Trigonal prismatic, and example is the TF7 2 minus, and then capped octahedron. So, the capped octahedron is an example where the primary coordination type is the Ligand octahedron. One of the face of the octahedron is capped by a particular ligand. Okay. So, these are different kinds of geometries, and primarily I took the examples of the transition metals primarily, okay, so that they are of most important to us in our the bio-inorganic chemistry or biological inorganic chemistry aspect. Whatever I said earlier in the previous slide can be seen a bit more with more clarity here. The 2 coordination, then you can see that kind of a thing, one ligand, another ligand in the metal center, trigonal with the metal with the 3 ligands, and the square planar with the ligand with the 4 with the metal ion with the 4 ligands, and tetrahedral metal ion with the 4 ligands, but they are arranged in not in a planar, in a non-planar, and which is very close to the tetrahedral kind of a structure. Then you have a 5 coordinated. This is the this 4 or square, and the one is like a pyramid. It's called, so it's called the square pyramid. Then you can see the example of trigonal bipyramid. This is trigonal, and this is the bipyramid. So, 3 in the row and 2, one above and one below. So, therefore, you have a, so you have by looking at the previous one and this, let us continue with the 6 and 7 as well. 6 coordinated, as I said, we have octahedral geometry. So, the kind of a polyhedral structure is also shown here. Trigonal prism is also shown. This molybdenum example is shown over here, and this will come as a antiprism. So, regular octahedron will be a trigonal antiprism, and this is a trigonal prism. Both are 6 coordinated. So, one is MoCO6, other is MoSCH2CH2S. This is a dithiolato tris. So, therefore, 6 coordinations totally. Then you have a 7 coordinated system. This is singly capped octahedron. So, you basically have an octahedron, and to this octahedron one extra is added to a face. So, MoCN 7 and continuation of this. This is pentagonal. So, 1, 2, 3, 4, 5. These 5 ligands are in one plane, and you have one above and one below, and that is the pentagonal bipyramid. So, the polyhedron will look like this, rhenium CN7. So, what did I talk to you now? Different geometries up to coordination number 7. Coordination number 2, coordination number 1 has no meaning. Coordination number 2, coordination number 3, 4, 5, 6 and 7. For 1 and 2 and 3, they are often they are found as a linear and the trigonal planar. When it comes to the 4, you have a tetrahedral and square planar, and when it comes to the 5, you have a trigonal bipyramid as well as square pyramid. When you come to the 6, you have an octahedron, you have a prismatic or trigonal prismatic. When you come to the 7, you have pentagonal bipyramid, and you also have capped kind of a octahedron. All these kinds of things are there. So, so that means when a metal ion is present in these metalloproteins, it would be stabilized into any of these geometries. So, the geometry is dictated both by the metal ion, its oxidation state, as well as the protein surrounding, both of these. So, please keep in mind that the geometries have an influence both from the ligand. In case of the biological inorganic chemistry, it is a protein, and the metal ion means its oxidation state. Both of these are very important. So, whenever we explain in future, we refer back to these basics, and at that time these basics will be of great use to you. So, that is why teaching you these basic concepts, though you are aware in your 12th and BSc etc., still I am trying to bring a kind of a recapitulation as far as the coordination chemistry is concerned. Since we assume or we consider that the metal enzyme, the metal portion is like a coordination complex. Now, let us get into another aspect of it. We talked about a ligand can act as a monodentate. We also talked about a ligand can act as a bidentate or multidentate. Now, when a ligand can act as a bidentate and both the centers are bound together, what it forms? It forms a kind of a chelate. Let me show you what I mean by that. So, when you have a metal ion and you have let us say monodentate ligand, so you have only this. Now, let me take a metal ion with two binding centers, and let us say you have the nitrogen here and binding together. So, you form a cycle. So, this is also called metalla cycle, and this is also referred as a chelate. This organometallic chemist will call this as a metalla cycle, and coordination chemists call as a chelate. And when you have, so now if I take another case where I have two ammonias and I have ethylene diamine. So, do you expect any change in its stability? Say the metal ion, same metal ion, let us say same N plus is bonded to two ammonias here and two amine moieties over here. So, the number of bonds from the metal to the nitrogen bonds, Mn bonds here are 2. So, here also Mn bonds are 2. So, do you expect any difference in the enthalpy of these two systems? So, there may be, I am sure when I asked this in the regular class, some people said no, we do not expect much difference. Some people said yes, that this will make a difference in this. Let me tell you, when you look at directly and compare, there are two bonds of the ammonia, two bonds with the amine, it should not expect much as far as the bond strength is concerned. But that is not true, because it is forming a kind of a closed cycle, so which is a chelate, and this gives a bit more stability than this molecule. If I have a metal with two ammonia versus I have a same metal ion with one ethylene diamine, both the nitrogens amines are binding, I would have greater stability found in case of the ethylene diamine complex. How? I will explain just in a while. So, let us in the meanwhile look at this. You have a copper with a tetramine complex. So, 4 ligands over there you can see, and instead you can have a copper with 2 ethylene diamines, will also be giving that. Now, if I take a copper ammonia complex and react with 2 equivalents ethylene diamine, what I would get? Copper ethylene diamine base, that is 2 and 2 plus 4 ammonia. Now, let us look at a bit more carefully. Okay. Here what do you have? On this side, the left side of this, you have one ion and you have 2 ethylene diamine molecules. Total particles are 1 plus 2, 3 particles here, and on this side you have 1 and then plus 4, 5 particles. So, 3 particles have turned to be 5 particles. What has happened? So, it is like a class having 20 people versus a class having 40 students. So, the teacher's control on 40 students would be obviously much less than his own control on 20 students. So, therefore, more number of ions, more number of disturbance. So, it is basically called entropy. So, therefore, this particular reaction is guided by the entropy positive. What happens? In the product side more entropy and the reactor side less entropy. So, entropy is changed, but enthalpy is not changed. So, because there are 2 bonds of the Mn here as well as Mn here, therefore, you do not have any difference in the, or no significant difference in the delta H, but significant difference in the delta G, because of the difference in the delta S. So, therefore, you are going from 3 particles to your 5 particles. If you look at the particle kind of a statistical thermodynamics, then you will understand if you study some physical chemistry there. But anyhow, right now you take it as granted that there are 5 particles generated out of the 3 particles, which means 2 particles are extra, that means they are in random motion. So, therefore, they will contribute to the entropy positive. Now, the same thing you can look at here. You see that delta H value for the 4 ammonias minus 53, for the 2 ethylene diamines minus 56, not much difference here. But whereas if you look at the delta G is minus 42.5 and minus 60 point, let us say 5. So, 20 almost 18 kilocalories difference. There is about 18 kilocalories difference in the delta G between a copper tetramine complex versus a copper bis ethylene diamine complex. But both these have got 4 copper nitrogen bonds. There should not be any difference. If it is only the enthalpy which is playing a role, there should not be a difference. That means some other factor other than enthalpy enthalpy is playing a role, and that is called the entropy. Now, you look at the entropy term. So, entropy term is minus 35 joules per mole and plus 13. So, going all the way from minus to plus. So, plus means more disturbance, more entropy, minus means less disturbance and less entropy kind of thing. So, therefore, the chelate effect is not really from a thermodynamically not really from the enthalpy driven one, it is an entropy driven one. So, it is an entropy driven one. So, though we do not expect when we look at the 2 ammonia bonded to the same metal ion versus an ethylene diamine molecule bonded to the same metal ion, though we do not expect much enthalpy change, there is a huge entropy change, therefore, it is more favorable, and such favorable effect is called chelate effect. So, that is what is the chelate effect basically means. So, that means when a ligand is bound through 2 of its, 3 of its or 4 of its ligating centers, you can expect such a kind of a thing to happen. Okay. One another very important aspect that I need you to see in these ones is as follows. Okay, we have looked at the different geometries in this. You know that different geometries will split the energy levels of the transition metal ion to differently. So, any transition metal ion, okay, the transition metal ion has d orbitals. So, we need to consider mainly the d orbitals primarily. So, the d orbitals, when you put in a field or in an atom, so in an atom the d orbitals or degenerate. Okay. But when you put this d orbital, the transition metal ion in the field of ligands, then the field of ligands will influence on the transition metal ion, and that will split the d orbital energy levels, which are having equal energy. There are 5 d orbitals are there, and these 5 d orbitals are degenerate, and these are called dxy, dyz, dzx, dx square minus y square, dz square. This you can see from any textbook and you will understand that. All of these in a free atom, they are having the same energy. But if I put some ligands, so some of them will go up and some of them will go down. Okay. Some decrease in energy and increase in energy. So, this is the energy gap. So, this energy gap is dependent on various factors. So, the d orbital splitting or energy gap is dependent on A, the type of ligand or type or nature of the ligand, and B, nature of the metal ion, in terms of oxidation state and ND level, etc., and C depends on the nature of the geometry, the type of geometry. So, there are various things are there. So, therefore, the d orbital splitting is dependent on from, let us say, 1, if you put an octahedral field. Okay. So, this will split into So, d phi of free ion, d phi and octahedral field of ligands, and this is referred as octahedral splitting, octahedral field splitting, octahedral field splitting. Okay. So, this octahedral field splitting obviously is dependent on the type and nature of the ligand, nature of the metal ion, oxidation state, in which n level, n is equal to 3, n is equal to 4, n is equal to 5, etc. N is equal to 3D, n is equal to 4D, n is equal to 5D, or the type of the geometry, and all of these aspects are involved. So, therefore, how does that matter? This matters because the electrons either may pair up into the lower energy level or may occupy these two, and as a result of that you get a situation of either a low spin kind of a situation or a high spin kind of a situation. Both of these are important in the biological inorganic chemistry because the metal ions will have either a low spin or a high spin configuration depending upon what kind of ligands are bound there, what kind of a field being created by the protein, what kind of a charge that we have in the metal ion, what is the oxidation state, all these kinds of things are very important, and that will reflect on the magnetic properties of this. Now, so in an octahedral case, let us look at and try to compare these things. Let us look at for a while the kind of a ligands will affecting this field is given over there. So, this is referred as a spectrochemical series. So, the way that this delta O splitting occurs is dependent on the, as I said, nature of the, one of the thing is nature of the ligands. Now, you see this is I minus, Br minus, Cl minus, F minus. That means, in the initial thing you have almost halides, in the next one you have hydroxo, oxo, water, etc., oxygen ligands. Then you have a pyridine, ammonia, ethylene diamine, bipyridine, these are all nitrogen kind of ligands, phenolphthalein. Then you have NO2, CS3, C6H5, etc., which is the carbon based ligands, Cn minus, CO. So, this delta O splitting is very least for the for the halides and the most for the cyanide and carbonyl ligands. So, this is very much influential on these ones. So, the halides, so delta O order, the delta O order is the halides will split less than the oxo ligands, than the nitrogen ligands, and than the carbon ligands. So, how do we explain this? Okay. Can we explain this based on the electronegativity principle? So, several of the students in the class have agreed on this when I ask question in the class, and several have very few have disagreed with this. So, in fact, it is those few who have disagreed with this are in right. So, you can explain this using the electronegativity only to a partial extent, not to a complete extent, but you have to invoke something called the pi acid or pi base characters of this. Note the sigma. Sigma bond is already there, bond is already present. So, what we are looking at is only the pi characteristic. So, I will be explaining in the next class what is how an acid, how a base. We are looking at the Lewis acid and Lewis base. Lewis acid is the one which has got a low lying orbital which is ready to accept a low electron pair, and Lewis base is the one where you have a pair of electrons, and the pair electrons can be easily donatable. So, this can be explained based on the pi bond, pi acidic kind of a character or pi basic kind of character. So, therefore, pi bonding characteristics are important as compared to the sigma bonding rather than just using the electronegativity thing. So, you can see that very clearly that you have a weaker field on this side and stronger field on this end. Okay. So, you will have with these ligands like halide you will have a less delta O value, and with these ligands, carbon based ligands, you will have a greater delta O value in this one too. So, I think in this particular lecture what I have talked to you is about the basic characteristics of the coordination complexes, how one define a coordination complex, what is a ligand, what is the charge, what is the oxidation state, what kind of ligands favor the kind of a binding geometries that we have. And then we have looked at the crystal field splitting which I talked to you just now for case of the octahedral, and the octahedral delta O splitting, it depended upon the nature of the ligands. It also depends upon the nature of the metal ion, oxidation state of the metal ion, and whether it is in a 3D series, 4D series, 5D series. All of these will influence. If you go from 3D to 4D to 5D, keeping the ligand same, you have a large split of the energy is also there. If you go from 2 plus to 3 plus to 4 plus, again the delta O will increase. On going from halides to the oxo ligands to nitrogen ligands to carbon ligands, also the delta O increases. So, all of these are important in understanding the magnetic characteristics and electronic characteristics of the metal ion present in the metal enzymes. They can form low spin or high spin, they can become diamagnetic or paramagnetic. Thank you very much.